Okay, finishing up with functions and models. Today we're going to talk a little bit about, not a little bit, a lot of bit about inverses. Okay, and we're going to polish up some of the things your pre-calculus teacher may have done with you and explain them a little bit more clearly than what you probably are already at. So, inverse trigs, or inverse functions and logarithm. Nobody likes logs, so we're going to go through that very quickly. But let's start with this. You're going to have to know what one-to-one means. What does one-to-one mean? Anybody?
Like in terms of a ratio? Like
No. In terms of functions. What's a one-to-one function? Kelsey?
Passes the vertical and horizontal.
Ooh, we'll come back to that in a second, but what does it mean?
That there's exactly one output for every.
Bingo. Okay, we'll get to that. HLT, mentioned that already. Inverse function. Now, this is the thing that I'm sure was a little shaky last year. All functions have inverses. Not all inverses are functions. Let me say that again. All functions have inverses, but not all inverses are functions. So let's talk about x squared. X squared is a nice pretty little parabola. When you take the inverse of that parabola, it's actually a sideways parabola, which would not be a function. I believe in pre-calc they do a lot about talking about inverses, but don't make the distinction between inverses and inverse functions. I might be wrong on that one. Yeah, we'll graph a logarithmic function. We'll talk about natural logs. Everybody know where natural log comes from? What is it?
Isn't it the log of e? Number e?
Say again?
The number e?
What about it?
It didn't. Isn't it?
He has its base, right? It's in its base.
Log base e.
Got it.
Yeah. So the log button on your calc. Oh, by the way, you're going to need your calculators. Get those out real quick. Let's take care of something before I forget. Hit the mode button on your calculator. Put that bad boy in radians. Radians. If you're in physics this year, who's in physics, they might have you flip it into degrees. I will try to remind you prior to testing that it needs to be in radians for this class. On the AP test, they make a point of telling you to put it in radians. The problem is, if it's in degrees, when you solve problems, you'll get answers. They'll just be wrong. So let's make sure that doesn't happen. Anyways, on your calculator, you have a log button. Find that log button. It's the button that says log on it. That is log base 10. You also have a natural log button, which we've already mentioned, is log base E. There are no other log buttons on the calculator. We'll address that issue later. We're going to talk about if there isn't a, let's say, log base 5 on your calculator, how are you going to solve a log base 5 problem? We use what's called a change of base. And then we're going to do some inverse trig, which for the most part, if you're rocking the unit circle, inverse trig should be easy peasy. Questions? Beautiful. Let's talk about one-to-one. We did this already. Kelsey already told us. For every x, there's exactly one y. For every y, there's exactly one x. That's a new term, though, injective. You've never heard that before, right? No, I haven't either. That's a new one on me. I don't think it's a real word. I think the author made it up. But he's dead, so I'm not going to call him out on it. I think he's dead. I don't know. Maybe. I'll look into that. Nobody cares. Hey, there we go. For every x, there's one and only one y. Ooh, wow, there's a lot going on here. Okay, first one. Let's talk about notation. This is a common mistake. The difference between this and this. What's the difference? Bashful, or is it you just don't know? Okay, that's okay too. The one on the right is an inverse function. That is the inverse of the function f. The one on the left is a function raised to the -1 power, also known as the reciprocal function. So if I want you to take a function and flip it over, I'll put the whole thing in parentheses, put a -1 up in the exponent. Well, we're going to be dealing with inverse functions, which are that -1 where it belongs. Okay, beautiful. I don't know if you covered this last year, but the domain of a function is the same as the range of the inverse. Have you heard that before? Yes? Outstanding. And the opposite is true. The range of a function is the same as the domain of the inverse. So let's suppose you get a big scary function and you don't know what the range is, but for some odd reason you know what its inverse is. You can always use the domain of the inverse. And then last but not least, you make a composite function out of a function and its inverse, you get x every single time. If you don't get x, they're not inverse functions. This I'm pretty sure you knew. It'll be nice when we get done with the review so I don't have to keep saying this is what I thought you knew, or do you know this? We can just go. Okay, so how to find an inverse function. Notice it says inverse function. First things first, you want to check to see if that inverse is going to be a function using the horizontal line test. Kelsey, what does the horizontal line test do for us? Which therefore, okay, it tells us if the function is 1 to 1, and if it's 1 to 1, then the inverse would be a function. Just a quick refresher, Alec, what does the vertical line test do for us?
It just tells us it's a function.
Good, tells us if it's a function. If it passes the vertical line test, it's a function. If it passes the horizontal line test, then its inverse is also a function. Now, that might not make much sense for those of you that are visual learners. Let's suppose our function is your friend and mine, Mr. X squared. Is that a function? Yes, it passes the vertical line test. Hot diggity. What's its inverse look like? Sideways parabola. Is that a function? No. Doesn't pass the vertical line test. So we can cut out that whole vertical line test for the function, for the inverse, by just saying the original function doesn't pass a horizontal line test, therefore its inverse is not a function. You might be saying to yourself, self, is he crazy? The inverse of x squared is the square root of x. And I know what that looks like. That's one of our mother functions. It looks like this. What's going on? Why did I take the whole sideways parabola?
Because you can't have a negative square root, but you're not square rooting it since it's the involved.
Because notice the x is a negative. We'll come back to this in a second. How do you find an inverse? If I give you a function and I say, hey, I'd like to know what the inverse is, how do you find it?
It's the -1.
Well, that would be the notation, but how do you actually find out what, suppose I give you I'll give you one in a second, but suppose I gave you a function f of x and it's some polynomial. How would you find the actual equation for the inverse of that function?
Put it in terms of like y equals x, and then you flip the variables, then you would solve.
There you go. Okay. Exchange x and y, solve for y. That thing you get is the inverse. So if I do that for x squared, y equals x squared. X equals y squared. Take the square root of both sides. Square root of x equals y. What did I do wrong?
Plus or minus.
Bingo. Plus or minus. When you take the square root of something solving an equation, you have to take the plus or minus, which is why we get the top and the bottom of the parabola. Versus when we use square root of x as a mother function. Hopefully I didn't confuse anybody. The difference between the inverse of x squared and the mother function square root of x are two different animals. Okay? Beautiful. They got all that. Yeah, I know. Okay, we did that. Mm-hmm. All right, good. So find that inverse, please. Hold on before you dive into that. Is that a function? Yes, because it passes the vertical line test. Is its inverse a function? In other words, does that function pass the horizontal line test? How would you do that? I'd graph that bad boy. What's that look like? Anybody? Bueller? What's the mother function that this function is based off of? Square root of x. So what did I do to square root of x to get the graph of this thing? What's the minus 3 do? Moves it to the right 3. What's the 2 do? Yeah. So this function looks something like 3 to the right, something like that. Does that pass the horizontal line test? Yes, so when you solve the problem and you figure out what the inverse is, you know automatically that that inverse would be a function. If you're not sure, then go find the inverse and figure it out that way. Andrew, what's the inverse? No. Did you do the problem? Math.
Inverse f of x equals x squared plus 3.
Can somebody confirm?
Yes.
Outstanding. Is that a function? It better be, because we already did the horizontal line test on this bad boy. Yeah, it's a parabola. It's been shifted up 1.5. It's stretched, or compressed. Who cares? Let's go. This is big. When you look at the graph of a function and its inverse, they are reflections of each other over the line y equals x. If we go back to that parabola, you can kind of see in that chicken scratch I made up there that if I draw the line y equals x through there, the blue would be the reflection of the black, and the black would be the reflection of the blue. The same thing is true here. I myself am very picture-oriented. I like to draw pictures of my graphs to do things like domain and range. This will also come into It's horrible English. Come into play, there we go, with working with inverses. It'll also come into play much later when we start doing derivatives. Along with that, we get one other tidbit of information. Let's suppose I've got a point on this graph here. That's 1, 1. Oh, that's a bad example. Hold on. Let's do 7. No, 7's too big. Come on, Reed, you got this. Let's pick a number for x. Let's pick 3. Okay, on that function, 3, 53. Can somebody confirm that? Is that right? 3 cubed is 27. 27 times 2 is 54. 54 minus 1 is 53. We're all on the same page, yes? Outstanding. Okay, so we know that that point, 353, is on f of x. Where's its corresponding point on the inverse? So this guy is on the black graph. Where's the corresponding point on the gray graph? I heard somebody say it. 53, 3. They switch. Okay. If you have a function, if you have a point AB, it gets reflected to the point BA, which is summarized there. That's also very big. We did this already, but we do need to talk about something in here. What in that little blue rectangle bothers you? Some of you had the slideshow in front of me. Just read my slideshow to me. Strictly monotonic. That's a fancy schmancy math term that means always increasing or always decreasing. If you've got a function that's always going up, it's going to pass the horizontal line test. If you've got a function that's always going down, it's going to pass the horizontal line test. If you've got a function that does both, you might have some problems. Like x squared. It's decreasing and then increasing, no horizontal line test. Bad. Okay, 1 to 1, pretty much, yeah, good, yeah, talked about that. Oh, logs. Anybody big log fans? Good, we're gonna go through this quickly. Logs come from the inverse of exponential functions. You can do this either way. You can start with exponentials and get logs, or start with logs and get exponentials. I like to start with exponentials and get logs. They're inverses of each other, so they're reflections of each other. We talked already about what exponential functions look like, so the log looks like its reflection. If the exponential passes through 0, 1, the log passes through 1, 0 every single time. Log base 5 of x, 5 is called base. You knew this already. And then we want to talk about all those simple properties. Breaking apart logs and putting them back together. Whoops. Teacher, your finger. The log of a product is the sum of the logs. The log of a quotient is the difference of the logs. That would be 1 and 2. The fun part comes in the change of base form. What if I have a problem that I want to solve that involves a log that's not on my calculator? How do I do it? I just happen to have one right here. What if I have log base 8 of 5 and I would like to know what the value is out to 6 decimal places? I don't know why I would go to 6 decimal places. I was feeling saucy when I wrote the slideshow. By the way, sidebar. AP standard. All answers that are approximate must be rounded or truncated to 3 decimal places. You understand what that statement means? Okay? I will clarify just in case you were afraid to say no. Let's suppose Andrew punches something into his calculator and he gets this. Okay? He gives an answer of this. Uh-oh. He's not going to get credit. It's got to go out to 3 decimal places. It can either be this or that. What's the difference? The top one is truncated. You just chop off 4 through whatever. That's okay. The second one is rounded. That's also okay. Which is a little contradiction because everything up until this point you've had shoved down your throat that you have to round correctly for your answer. College Board doesn't care. Truncated or rounded, it doesn't matter, but it's got to be 3 decimal places. Okay. As far as the log goes, you can decide, do you want to work with natural log or do you want to work with log base 10? At this point, most of you are probably going to choose to work with natural log. So if I want to figure out what the 6 decimal equivalent of the log base 8 of 5 is, I would do the natural log of 5 over the natural log of 8. Plug that into my calculator and get an answer. Do that, please.
Only because I didn't know it was there. I never used that before.
Mr. Smarty Pants up here in the front row has pointed out that in the, what, math menu?
Yeah.
In the math menu, there is a log base whatever. That'll make your life a little bit easier. Sorry. What's the answer? 0.77. Okay, so we'll go we'll truncate. If you did it as log of 5 over log of 8, you get the same answer. Did you get the same answer using the base thing? So if you found that thing in the math menu, you'd be good to go. Can somebody please acknowledge what I did with the background on this slide? Okay.
Is that your base?
No. No. I got off the crack. I didn't play it anymore. Okay. It's a 12-step program I entered. It took me about 6 months to get to step 5, and then it was pretty fast after that. This kind of hurt a little bit, even including it in the slideshow. Brought back some bad.
Were you in an anonymous support group too?
Was I what?
Were you in an anonymous support group as well?
I was. I have a coin now. Yeah. COCA, Clash of Clans Anonymous. It's a very proud moment in my life. It's probably going to be my next tattoo. Yeah. Inverse trig. If you're rocking the unit circle, this shouldn't be a big deal, except for one small pesky thing. Remember that fun?
Whoa.
Yeah, there's a lot going on there. Let's unpack this bad boy. I would assume that if I asked you what is the sine of pi over 3, most if not all of you would rock that. Yes? Just for giggles, what's the answer? Square root of 3 over 2. Hot diggity. That is taking the sine of an angle and getting a trig value. Going backwards, however, sometimes causes problems because there are a whole bunch of different answers. There's only one pi over 3 on the unit circle. So we're good to go. However, there are a lot of places on the unit circle where the value of the sine is the square root of 3 over 2. So we have to narrow it down so we don't keep puking out answers. That comes from this, also known as quadrant restrictions. Okay. Now, how do you remember this? You do the following. Notice that every one of those has quadrant 1 included. That's the positive answer that you're looking for. Every function also has a second quadrant, which is negative. Which one is it? Well, the way to remember that is that you're never going to use quadrant 3. Quadrant 3 is not represented up there. So if I take the sine, for instance, I know that the sine is positive in quadrant 1, so I'm going to use quadrant 1. Where else is the sine negative? The sine is negative in quadrants 3 and 4, but quadrant 3 is verboten. Therefore, we have to go to quadrant 4. And that's where my two answers come from. One comes from the quadrant 1, the positive answer. One comes from quadrant 4, the negative answer. One other thing to note is all of a sudden we changed. When we start dealing with inverses, we don't deal with that fourth quadrant being 3 pi over 2 to 2 pi. We deal with it as being negative pi. So you go from 0 either upwards to pi over 2 or downwards to negative pi over 2. Anybody know what that stands for? Just for giggles, it doesn't really matter. It's not a typo. If and only if. Okay. It's irrelevant, just want to point that out. Okay, so what's the arc you know arc, right? Arc cosine, you're okay with that? Anybody not? Never seen that before? We're good? No? Okay, that's the same thing as just another way of writing the inverse cosine. Why they have two methods, I have no clue. Okay, where's the cosine equal to 0? Hello, Mr. Everett, how are you? Hey, come here a second. So this is the guy that screws up everything. Mr. Everett, this is my calc class.
Hi, everybody.
My calc class, this is Mr. Everett. The mistake maker. Okay, go play in traffic now, youngster.
See you later.
Goodbye.
Traffic now.
I'm trying to mentor him. It's not going so well. I don't think he's going to make it. Oh my God! All right, hold on. Blah blah blah. Yeah, get that. Go ahead. Okay, calculator, unit circle. Great. Okay, hold on. One last thing that's important. What if it's not on the unit circle? Okay, 1/2 pi over 4, negative pi over 4 on the unit circle. But if it's not on the unit circle, you know how to handle that. You write a triangle. You draw a triangle. Yeah, bing, triangle. Pythagorean theorem. Solve for that third side, and you find all the others. Almost done. What if you're not given numbers? What if it's an x? That's okay. You can solve Pythagorean theorem using an x because you just do x squared plus that other thing squared equals 1 squared, and solve for that other thing. You get 1 minus the square, or 1 minus x squared square root of that whole thing. And then, anybody get the joke?
Yeah.
What are those?
Logs.
What kind of logs? They're natural logs. Have a great day, everybody. See you on Thursday.